I had a question about the homework.
Yeah.
Every time I've tried to do the homework on Cengage, if I answer the first question and I click next question, no other questions show up, and I
Hmm.
can't submit any of the questions.
So this has been happening for the last 5 homeworks?
No, just this last homework that has happened,
Oh, okay.
and I sent a message saying I wanted it extended, but that was just to try to tell you.
Oh, I usually get notifications or like emails from that, and I didn't, but I will look into that after class.
Okay.
Yeah. If this happens again, email me right away. I know the WebAssign should have emailed me when you send an extension, but it doesn't always, I guess, now apparently. But I'll see what we can work out.
Okay.
I've had a student where that's happened before, and then the next day it just like worked. Or they reached out to, usually they reached out to support through Cengage.
Okay.
All right.
Sounds good.
Do we need to restate the question? Okay, let me get to that in 1 second. Abby, I'll answer that question. So quick announcements today. Homework 5 is due this evening. Text corrections are due tomorrow evening. I wanted to give you guys an extra day because I really wanted you all to be able to get those done. From now on, I would really, really enjoy it if you all would submit your assignments as one PDF, especially exams. Adobe Scan is an app that is on your syllabus that I've mentioned it before. And if you just like take a picture, then hit continue, it'll just add another page as a PDF of the next page that you take a picture of. And there's lots of other scanning apps. It just makes my life go a lot faster when there's one PDF instead of like 9 different pages that aren't even PDFs and they're JPEGs and they take forever to load and they're all in different orders and it's very confusing and they're sideways sometimes. Oh God. It just helps me a lot and it's a little more professional turned in as one single PDF. And then today we finished 1.8 last time. And so in 1.7, so now we're moving on to chapter 2 and 2.1 and 2.2 is what we're going to try to get through today. This picture is also not a picture of Duke, but what I would think a picture of Duke's puppy would look like, right? So like that's the puppy, that's Duke, right? Totally could be him. So Abby, when you asked to restate the question and rework it for test corrections, pretty much. Let me open the assignment page that I set for submissions. Test correction PDF. Reloading. My computer's trying really hard. Yes, so right, I say clearly include the following for each question. So the problem number, so like problem 1, and then state the question, right? So if you're asked to simplify and express your answer in rational exponents, I want you to write that bit out and the problem. None of the problems should be that long. And then your corrected answer is all the work and also the answer, right? You can't just give me, just like in your exam, you can't just give me an answer. You need to provide proof to that answer and why it is the answer. Does that make sense? So I guess answer to your question is yes. Does anyone else have any other questions about homework or test corrections? Okay. I'm going to move on to 2.1. Oh God. Hold on. There we go. So chapter 1 was like kind of a lot of different things, right? We already knew about equations, and then we talked about function notation. What's it mean to be a function? And we also got into like functions in the real world when we talked about in section 1.8. That was like all about like applied problems, which are my favorite. I love 1.8. It's my favorite section. So now we've kind of built ourselves up, right? We know a lot of background about solving inequalities. I know about domains and ranges now. I know about net change. I know what's a function, what's not a function, and independent variables and stuff like that. So now I can really talk about the specifics of what's inside of a function, right? So we've talked about net change. So Thursday doesn't really seem like an orange. Oops, I didn't mean to do that. Let's do a green for Thursday. So if you want to think of like net change as like a little kid, average rate of change is a cool older brother, right? So it is March 4th, 2021. It's March again. Right, so in 1.7, we discussed how to look at graphs and see if it's increasing or decreasing, right? In this section, we're going to take it a little further and talk about how fast a function is increasing, at what rate is a function decreasing, right? If we think about like my distance away from something, if I'm increasing or decreasing, I can think of that of like almost like speed, how fast away I'm going. Speed varies. I could go 1 mile per hour, I can go 10 miles per hour. That's kind of like what I like to equate an average rate of change to. And really, it sounds like a big clump of words, but if you just break it down, it's a rate of change. So like some amount is changing, the rate at which it's changing, and then average. You're going to take lots of little sections and I'm going to average them all together. Okay. One moment. Okay. The rate at which a function increases or decreases can vary dramatically. For example, think of a runner. When they start running a race, that's what I meant. Their speed quickly increases, then stays at the same as they run, and then quickly decreases when they finish the race. When I run, it does not quickly increase. It stays pretty slow, if I'm being quite honest, right? So we need to like somehow quantify this change in how fast this runner is running, right? So a lot of math is approximations. So for that reason, we can say that a good approximation of a rate of change is, what do you guys think it's going to be? It's the average rate of change. And you're like, Mackenzie, that doesn't make sense. It's just the average rate of change. We have different rates of change. You'll learn about another one later in this class, and then a third one if you take a similar calculus course to 141. I think maybe, I don't know what it is. The other calculus course is. But in this course, we're going to first focus on the average rate of change, right? So let's define it. So the average rate of change, I also like to call him A-Rock because who likes to write all that out? So the average rate of change of a function y equals f of x. So remember, we just talked about function notation. Y equals f of x means y is a function of x, right? So much of the homework that you're going to be turning in this evening, y would be my dependent variable, x would be my independent. So I can get all of that from just seeing that y equals f of x. It's kind of cool, right? Okay, back to what we were talking about, right? The average rate of change of a function y equals f of x between x equals a and x equals b is, so we can say that a rock, we don't really have like a symbol for it. Well, not necessarily, we will in a second, is going to be the change in y, so the change in my outputs over my change in x. In mathematics, does anyone know what the symbol we use for change? Does anyone know? Yeah,
Isn't it like the triangle?
yeah, you guys are both right. And that triangle is actually called delta. So it's the Greek letter delta. So we can say change of y over change in x. So it's delta y, delta x. These aren't like some variables here. These are like just explaining change in y over change in x, right? And then to take it further, because like what delta x, delta y, I don't know. How can I like figure out what the actual rate of change is using that? So if I'm taking the change between x equals a and x equals b, so I'm going to do b minus a for the change in x, and similarly in the numerator, I'm going to do, excuse me, f of b minus f of a, right? Does anything look familiar about this formula? Is there anything that we've seen before? There's lots of different answers. There's not one specific one that I'm looking for. Does anything look familiar in this one? B minus A looks familiar from what? What about this top part? Oopsies. Does that look familiar to anybody? What does that look like? Not completing the square. I don't have anything squared at all. But good guess. What's another formula that has the word change in it that we know? You guys had homework on it. Charlie, are you talking? Ooh, yes, who's talking?
Keep, change, flip, or no?
Like dividing of two. Close. We would use it. I was asking Charlie if you were referring to the whole thing or just the numerator for the slope. Yeah, right, the whole thing. So it's not the slope that we would traditionally think about, but it's going to be the slope between A and B. Right, because if you want to think about like it as x equals A is like x1, x equals B is like x2. All this is just y2 minus y1 over x2 over x1, which is just the slope. Right, and the reason I say slope between x equals A and x equals B is because we don't always have the same slope between every 2 points of a function. All right. And then this top little bit right here, that actually is the net change between A and B, right? So net change, that's something that you guys are going to be asked to find a lot this section, and in your homework, I'm pretty sure it's due today. Right, so f of B minus f of A. Right, so what does the average change kind of look like graphically, right? So let me get draw this. And then we're gonna have what a better curve. There we go. So this is just gonna keep going. That's gonna keep going. And let's call that's gonna be A. So this makes that f of A. And this is going to be B. Making this f of B. Make that point. All right, so my change in x is going to be this distance right here, B minus A. So this is going to be my delta x, where this is going to be my delta y. Right, so does anyone have any fun way to remember slope at all? Right, how do I remember that it's delta y over delta x and not the other way around? You guys have like a fun little way of memorizing it? I always remember rise over run. Has anyone heard of that? Yeah. Right. So, right, my rise, I'm going up, rise, and then run, I'm running over. I can't run up a wall, but I can run down the street. All right. So that's how we can remember that it's going to be y on top, right? So what we said before is that delta y over delta x. So kind of want to re-emphasize this, is the slope between the points A and f of A, using function notation here, and B and f of B. All right. How are you guys feeling about average rate of change so far with the definition in this little picture? I just think we can handle doing some word problems. Okay, great. Love to see it. So let's talk about Hannah. So Hannah is installing a new Italian ceramic flooring into her house. Amazing. Below is the total number f of x of tiles she has installed after working for X hours. So f of x is our output, it's the number of tiles that she's laid in that many hours, right? When we're doing these word problems, they're not going to say, they might not say from this hour to this hour. They might say something like in part A, to find the average rate of installation. I should say average rate of change, but the textbook doesn't, so I copied it wrong. Of change of installation in the first hour, right? So in the first hour, I'm going to have two x's. Let's call my starting point x1, and I'm going to have my end point x2, just to clarify which x is which. Okay? And we usually do that with subscripts. So if I'm going to find the average rate of change in the first hour, what two x values should I stop and start at? 0, 1, right? Oh my God, why is everyone emailing me right now? Right, so I'm going to have my average rate of change, and it's going to be, is it going to be f of 1 or f of 0? I write first. F of 1, right? The bigger input first. Minus f of 0 over 1 minus 0. I go up here and I find f of 0. It's 0. That makes sense. And f of 1 is 21. So I'm going to do 21 minus 0 over 1. And that gives me 21. What types of units am I going to have on this? Because 21 doesn't really make sense. Not just tiles. You're on the right way. Tiles per hour, right? So we usually write tiles over hours. And a good way to figure out our units, right? This is tiles divided by hours. That little division we usually think of per, right? Just like Abby said. So the top, my F's, these are in tiles. And then, so this is like 21 tiles. My 0 tiles is going to be 21 tiles over 1 minus 0 hours, which is just 1 hour. And that's how we're to know what units to do and which one to put on top of the bottom. Okay. So now we're asked to find the average rate of change of installation in the first 4 hours. So what do you guys think our X1 and X2 are going to be? I'll give you that X1. I kind of just wrote it. Never mind. We're just going to do this. I got so excited. Right. So now when I say the first 4 hours, I'm talking about between 0 and 4. That makes sense. I'm going to go over here again. If you want to write out the formula when you're doing these, just to like kind of get you into remembering it. And then what's my f of b? It's going to be f of 4 minus f of 0. 4 minus 0. We'll go up here. What is that? 189. So 189 minus 0 over 4. And I think that gives me 47.25, again, tiles per hour. Units is really important in this section, just kind of how I emphasize that in 1.8. Word problems, when they give you hours, tiles, miles, kilometers per second, you got to put in your units in your answers or we're not really 100% correct. Let me underline everything so we know how to include our units. Okay. So I've done a lot of the talking for this problem so far. So can someone or a few of you walk me through how I should do part C, which is to find the average rate of change of installation in hours 6 to 8? Ooh, that's a really good question. Why we won't round it to 47. Because when we're usually talking about average rates of change, we're just talking about a speed, right? Or how fast is she moving? Well, she's working 47.25 tiles per hour. That's totally fine for us to have decimals in this situation. Does that make sense? Mm-hmm. That's a really good question, Arnold. So who can help me with C? How can I find the average rate of change between hour 6 and hour 8? A-Rock. See if I can fit everything in here. What should I do first? Mm-hmm. So Abby wrote f of 6 minus f of 8 divided by 6 minus 8. And I assume that 6 minus 8 is the whole thing under the denominator. Right. So traditionally, I do agree with Abby, even though we're not doing the bigger number first minus the smaller number, because I'll show you why. When I do f of 6 minus f of 8 over 6 minus 8, what is, here's 6, here's 8, 245 minus 403 divided by, what is that, -2? And then that number should shoot out to be, right, it's because the negatives cancel out. Oh my goodness. Sorry, negative, there's only so much mental math I can do in my head for a day. So I get -158 divided by -2. And those negatives cancel out. Let me cancel those out. Right, negative over negative is just a positive. And I get 79 tiles per hour. So the order doesn't necessarily matter, but I will say when I ask you to state the average rate of change, but say like between x equals a and x equals b, I do expect it to be b minus a. And the order really matters when we're working with net change, remember? Because that only has a negative. No, it's not an absolute value because that's a good question. It's not an absolute value because, right, absolute value, and that means I would always get an average rate of change that's positive, and I don't always have that. I could be decreasing. That is where we would have a negative average rate of change to be fine. It's just kind of better practice to do b minus a and f of b minus f of a, just to kind of be safe. So your net change and your average rate of change kind of follow with it. It's more of a formality, but if you do mess it up, it's not going to be the end of the world. Does that make sense? It works when you kind of just need to match up these things, right? Like f of b needs to be over b. And yeah, right? Because it's a minus b. That's the kicker, right? If you flip one of them on the top, you need to also flip the one on the bottom, whoever you're doing first. They need to be the same. That way, if a negative pops out, they cancel each other out. Good observation, Griffin. That's why it's kind of, we just tell you guys to memorize this. I don't like telling you guys to memorize something. But to doing the large number. And it helps that we know net change to be f of b minus f of a anyway. So we're just adding just a denominator on. So it's not that much more to add on. All right. How are you feeling so far? Thumbs up, thumbs sideways, or thumbs down? Nice, nice. Okay, love to see it. All right, cool. So now let's talk about farms. My favorite thing. I grew up on a farm. We have beef cattle and I love them. All right, so you're given this table in your textbook of the number of farms in the US, right? And obviously this is of thousands, right? So there's not only like 2,000 farms. There's like that times 1,000. We just scaled it down a little bit, right? Ooh. You'll often be asked to sketch a plot of the data. Hold on one second. Oh, an ice cube. Whew, okay. All right, so we're asked to draw a scatter plot. Right, drawing pictures is a really great way so that if I do somehow make an error in my ways, I can then look at the data I was given and be like, does that match the picture that I drew? Like, just gives us kind of like a visual representation. I cannot draw a straight line. There we go. A visual representation of kind of what I need to make sure my outputs of my data work. I'm just rambling right now. Okay. So if I kind of do a loose sketch, so what is this? Like, where we start in 1850, 60, 70. Something like that. Okay. Let's do these as little. So it's going to kind of work itself up like this. This is like the general gist of it. We're just doing this for time's sake. Who's the largest? Do, do, do. Okay, it kind of looks like that. I'm not very good at sketching these things. All right. And now we're asked to find the AROC and the number, so the average rate of change, and the number of farms between the following years, 1860 and 1890, and 1950 and 1970. All right. So I really like to highlight or circle the data I need. So 1860 and 1890. 1890, what was it? 1950 and 1970. Okay. So let's do I first, right? My AROC is going to equal F of 1860. Oh, that's 1690 minus F of 18. Oh my God, I'm messing this up. There we go. 60. 1890 minus 1860. All right, cool. And what is those function values? 4565. 4565 minus 2000 something, 244. Over 30. Great. All right, and then when I do that subtraction in division, I should get, I don't really want to round that. Let me see. 4565 minus 2440 divided by 30. Oops. Equals divided by 30. There we go. 70.83. I'm just gonna call it that. I usually like to just round to the second decimal, right? And what would, so I did most of that for you guys, but what would be my units on this? What would be my units of my average rate of change? Let's scroll up here and look at our data as given. What do you guys think our units on our average rate of change would be? Anybody? Well, when we're doing average rate of change, I kind of need 2 units. Farms per year, it's a good one. But am I increasing 70 farms per year? Remember this guy? So that one, that tells us that it should be 1,000 farms. Okay, I need more space. Thousand farms per year. So 70.83 thousand yards farms. Oh my God, per year. Okay. Box this answer in. Does that make sense why it's 1,000 farms per year? It's because we're given that
So
farm.
because it has the time like times 1,000, that's the only reason why you put like 1,000.
And sometimes the problems, yeah, absolutely right. Sometimes
So if they
it'll,
have like 100, what you do? Just put hundreds like that.
yeah, 100 farms per year.
Oh, right.
Good question. Sometimes it might tell you like in thousands or in hundreds or something like that, in millions, just so it's like easier numbers and you just don't have like 5,000 zeros there that you have to deal with. It's more of a convenience sake. All right. That was a really good question. So for number 2, now we're asked to do 1950 to 1970. So do AROC F of 1970 minus F of 1950. Whoopsies. There we go. 1970 minus 1950. Right? So I'm going to scroll up and look at my data again. So I'm going to take these two guys. So 2780, 80 minus 5388. Over what, 20. All right, so then 2780 minus 5388 divided by 20, and that's going to give me negative 130.4 thousand farms per year. You can also write just per year instead of divide by year. Well, that's a negative number. Is that okay? Can I hash? Does that make sense for it to be a negative number? Right, it just means a decline in farms. And we can even go back at our data and see that, oh, I was over 6,000 and I was moving down. So yeah, that makes sense that it would be negative. I'm decreasing, I'm declining. I'm just going down this hill. So I'm probably in this area. I was better at drawing these graphs and we'd be better at seeing this picture visually. Right, so if I'm decreasing, I'm gonna have a negative average rate of change. But if I'm increasing, like I am here, I'm gonna have a positive one. This is also just another way. So if you do accidentally flip f of b and f of a and b, like we did in a previous problem, this one right here, part C, that you're just consistent because we got negatives and top and the bottom. You're like, oh, but this was increasing. That's where that negative comes out and cancels each out. So I do get something positive. In this case, I got something negative. You might like be like, oh, did I mess something up? Like it's negative. That's kind of weird. Maybe, I don't know. It's okay for things to be negative. Just make sure that your work is correct if you feel like you made an error. But you guys are smarty pants and I believe in you. Sure is so squeaky. Okay. So,
I have a question.
oh yeah.
So for these type of problems, we use the same formula like every time, like F, and then plug in the like, you know what I mean?
Yeah. There's f of b minus f of a over b minus a.
Will there ever be a situation where like F is not like determined? Like, you know what I mean?
Like I might give you like f of b equals this, f of a equals that. I don't know. Maybe. We're going to talk about a situation where like a special case of average change after this problem called average speed. And I think that'll answer your question.
Thank you.
So I think you're getting a little ahead of yourself and getting too excited. But good question. I'm loving all the questions. All right, cool. So we've kind of just been finding the average rate of change between two numbers over and over again. But we can also be asked to find which decade did the number of farms experience the greatest average rate of decline, right? So what is this saying? Is it asking me to find every average rate of change between each consecutive decade? But it says average rate of decline. So what should I focus on? Not percentage, negative, right? I want to look for kind of what we were talking about right here. It's saying Which decade has the largest, a bigger and large here we're saying, oh, it says most negative, I think. Yeah. When I say most negative, I mean like a negative number that is large in the sense of like negative 1,000 is a more negative number than -1, right? So the most negative number. Which decade has, I wrote has twice. The most negative, A-Rock. Right? So we can go, I'll give you time to write that down. We can go look at our data and our poorly drawn scatter plot written by me to figure that out. So when we talk about average rates of change, we talk about slopes, right? Usually think of like on a straight line, slope between 2 points. But when I'm talking about a more negative average rate of change, is that going to look like a negative slope kind of looks something like this? Is it going to look like that? Or is it going to kind of look like that? So it's going to look like A or is it going to look like B if it's the most negative average rate of change? Ronald says A. Elizabeth says A. Why A? All right, it has the steepest decline. Yeah, B is kind of closer to being flat, which is flat is like a slope of 0, right? The steeper the slope, the larger or more positive and more negative the number is. I say, again, more negative because like -1 is a bigger number than -1,000. So I don't want to say the bigger number. All right, so we want the steepest slope. Another way we can look at that is like kind of like the biggest decline. So this one's like kind of, oh, sorry. So when did we start declining? That looks like our biggest guy. So from 1920 and all the way down until $1990. That's my decline period. Don't look at my scatter plot, it's really bad. Right? So then I can go here and be like, okay, 640, 540, maybe. And I would keep going up. But then I look right here. That's a really big change. That's over 1,000 change, right? If you had more time to draw a scatter plot, this might be easier. But we can see right here, do you see how like the change between these 2 years is a lot more than all the other ones? Right? Like this one is like not even 100, but this one's like over 1,000. So that is our steepest decline. I don't know what happened in the 50s. I'm not surprised there was a decline in the 20s. That was when the Depression was. No idea what happened in the 50s. War? Was there a war? I have no idea. So using that, we can say between 1950 and 1960, farms in the US showed the greatest decline. Or average rate of decline. Using words from the problem. Just so I know I'm not saying something that I mean to, like saying something else when I mean something else. Okay. How do you guys feel about our farm problem so far? Thumbs up, thumbs sideways, or thumbs down? How are we feeling? Vibing up. Nice to see it. Love to see it. Okay. I'm going to take everyone else's silence as thumb sideways. Okay, so a lot of times average rate of change you're going to be talking about, a way to remember it is miles per hour. It's because average speed of a moving object is just kind of like a special case of average rates of change. Right, so if we think of the change being distance or over time, that's an average rate of change. So we can say that the average speed of a moving object, car, person, airplane, time between times t1 and t2 is, so we're going to call this AS. What do you guys think it's going to be? Let's do our delta one first. So average speed. What do we think it's going to be? Instead of delta y over delta x, it's going to be change in, what's my output? Think about the units when I'm thinking about average speed: miles per hour, kilometers per second, centimeters. What are all of those things? They're different. They're measurements, but distances. Different ways to measure distance. I was really harping on one answer, which I shouldn't have done. But thank you, Alyssa. Right? Our distance, and then miles per hour, kilometers per second. Right? So it's a change in distance over a change in time. Right? And then if I want to use we're told that S is the distance traveled in time, T. So instead of using f of b minus f of a, because I'm trying to find the average speed between times 1 and time 2, so it's going to be s of t2 minus s of t1, right? I can call my function whatever letter I want, s, n, c, g, h. We just usually like to work with f. F stands for function. It's pretty easy to remember. So that's going to be our equation for average speed. All I did is I just changed my b's and my a's to t1, t2. And instead of just talking about an arbitrary function, I'm talking about s, a speed. Well, here actually it says s is the distance, which I actually think we do use s. Okay. So from that definition, we can talk about objects dropped in a vacuum. Vacuum means there's no air, so no air resistance on it, right? Right, in a vacuum, a bowling ball and a feather fall at the same speed because air resistance is not there. Have you guys ever seen that video? It's pretty cool. The distance the object falls in t seconds is s of t equals 16t squared, right? So s of t is my output, t is my input, where s is in feet. Are we given what t is in? Oh, seconds. And t, seconds. So our answer we already know is going to be in feet per seconds, just by that already. Find the average speed of a bungee jumper during the first second of the jump. All right. So our little guy, he is going to fall, fall, fall. There he is. That's him jumping on his bungee. Okay. Okay. So for the first second of the jump, what is my T1 and my T2 going to be? I almost wrote it again. I also write my T's kind of curved so they don't ever look like plus signs. That's just a mathematician thing. So if I'm trying to find the average speed of the bungee jumper during the first second, what is going to be my start and my finish of that interval. We've done something similar. We talked about the tiles. So if it's during the first second of the jump, so what second am I going to end on? T's in seconds. Am I going to end on the second second? Or the third one? Why would I end on the second second? Jaden says 1. Ronald's taking them back now, right? I'm going to end on my first second, right? If it's during the first second, just similar to how we were talking about tiles over the first hour, I'm going to end at the first hour because I've been working that whole time. I've been moving that whole second. I'm just capping it off once that second is over. So if T2 is 1, what do you guys think T1 is going to be? 0, right? Great. Thank you for the participation. Right, so we're going to use T1 and T2 equaling 0 and 1. So that means that our average speed is going to be S of 1 minus S of 0 over 1 minus 0. So instead of just be given this function I equals this, now we're given a function, which I think was Jaheem's question. If we're going to have to like plug in a function. I don't want to take words out of your mouth, but I think that's what you were asking. So I'm going to go over here and look at my function. So I can do 16 1 squared minus 16 0 squared, right? Just plugging 1 in for t and 0 in for t into my function. And then 1 minus 0 we just know is 1. 1 squared is 1, so that just gives me 16 times 1. Anything times 1 is just itself. Minus 0 over 1. And I get 16. What are my units on this? $16 isn't just an answer, right? Feet per second. Beautiful, right? And that's how we're going to find it for the first second, right? Now, what if we're asked to find the average speed during the third second? Sounds a little trickier. What would T1 and T2 be here? The first second, T1 was 0 and T2 was 1. Kervin says 1 and 2. It's the third second. So from 0 to 1, Ronald says from 0 to 3. First second, 0 to 1. Second second, 1 to 2. Second second, 2 to 3. Yeah. So 0 to 3 is going to give you the average speed for the first 3 seconds. So this is just the third second. Does that make sense? Right. That would be the average. I mean, that would be the average rate of change of those 3 sections. Did we ask that question? No, I think we're just done for this one. But in a sense, right, there's still average speed is just a special thing of average seconds. But once you start grouping in bigger and bigger intervals, your average rate of change is going to differentiate. So we're going to do between time 3 and time, T2 and T3. Also think about it as like the first second starts when I turn on my clock and then it ends after 1. Like the first hour afternoon, like 1, right? You start at 12 and it's like kind of at like time 0, right? Like 0, 100 hours if anyone's in ROTC. Anyways, So our average speed is going to be S of 3 minus S of 2 over 3 minus 2, which is just going to be 16. 3 squared minus 16, 2 squared, which is going to be, again, just over 1. 3 squared is 9, so 16 times 9 minus 16 times 4. It's going to be really embarrassing. Okay. Over 1. 16 times 9. Oh. I'm an applied mathematician. I don't know these. Oh, it's 144. Minus 64. What is it? So then 140 minus 60, which is 100 minus 6 minus 20. So 80. What are my units again? Feet per second. Always have to add my units on there. I'm not 100 yet. Okay. How do you guys feel about, this one's a little tricky with the wording of the problem. The difficult part about these word problems. I got 80 feet per second too. How are you guys feeling about average rate of change and average speeds? Thumbs up, thumbs sideways, or thumbs down? The reason that we chose 2 to start with is because we're told during the 3rd second, right? So during the 1st second, they kind of set you up. Okay, that's just the 1st second between 0 and 1. Well, the 3rd second, it's an interval, right? So from 0 to 1, that's 1. I'm only talking about during 1 second, kind of like how we were just talking about during 1 decade was between 50 and 60. So the 3rd second is going to be between 2, and then when I finish that 3rd second at 3. If you think about it, how like the first hour of the day doesn't happen during 1 a.m. It happens in the 12s. That's a kind of the best way I can describe it. Time and indices for time is, we start at 0 instead of starting at 1, which makes perfect sense, but yeah. Okay, cool. So we are done with this section. So let's bop over to 2.2. Oh my God, I uploaded these notes and everything worked at the beginning of class. Okay, now it's opening. Great. It is still Thursday, March 4th. Do we have class on Pi Day? Hold on, I need to figure that out. That's really important to me. Do we have class on Pi Day? Oh, we don't. It's a Saturday. Sad. I love Pi Day. Okay, cool. So now we've talked about average rates of change, average speeds, and stuff like that. So now I can talk about different types of functions and differentiating them by their different rates of change. Okay. So last section, we saw functions that had different rates of change during different intervals, right? I was increasing the amount of farms, Great Depression hit, they decreased, and then we came back up again, right? All changing up and down. So I kind of give a spoiler, but what type of function will we have the average rate of change is the same on each interval? What do you guys think? When I draw the slope between 2 points, what do I usually draw in between them? Do I draw a squiggly? What do I draw? If I just want to do the slope, represent the slope between 2 points, how would I connect those 2 points? A line, right? A straight line, right? And we call these lines linear functions. It has the word line in it, right? So a linear function is a function of the form f of x equals mx plus b, which I think most of you are fairly familiar with, or I hope so, right? Where m and b are real numbers, right? In this course, we don't deal with imaginary numbers. I consider them non-existent. All right. So I like it to be of this form. And then we'll talk more about linear functions and different ways to write them. But for now, we're just talking about mx plus b. All right. So, and note that x is to what power? What's x's power? 1, right? Not -1, not 2, just 1. Okay, so keep that in mind. So real quick, just knowing that a linear function has that form, let's look at these 4 functions, and I want you guys to tell me, are they linear functions, right? So for A, f of x equals 2 plus 3x. Do we think that's a linear function? Griffin says yes. Everyone says yes. Why? Who can tell me why? Gotta tell me these whys. Right? I have x is a power of 1. Well, it's not, I have 2 plus 3x. Why? This is, I should have mx plus b. So just because my x is power 1, I can do it. Right? M and I can switch the order. It's just addition, right? Yeah, I can just rewrite it. So yes. What about b? I have g of x minus 2x plus 1. Do we think that one's a linear function? Ron says yes. Why? Why is that one a linear function? Why do you all think it's a linear function? I have a negative now. Can I have a negative in front of my x? Yeah, heck yeah, I can. I just need, no, negative numbers are real numbers. What about C? hx equals 3x squared plus 1. No. So no, x can't be squared. What kind of function is that? Does anyone know? It's a quadratic, right? Perfect. When it's x squared. We also call it a polynomial. I think polynomial has a lot of bigger meanings. Okay, what about kx? I have 1 minus 5x over 4. Ooh, I have division involved. Griffin says yes, Ronald says no. A conflict. I have so much energy now, I'm so tired. Which is it and why? Who can tell me why? Griffin's telling me rate of change is 5 over 4. What if I rewrote it like this? Then it's yes, yeah, right? That division there looks kind of scary, but it actually still is a linear function because I can write it like this. So fractions are fine, just as long as they're fractions with just numbers, not with x in the denominator. Just want to keep x up top in the numerator, keep it happy. Right? Perfect. What was I gonna say? I had something really cool to say. No, I forgot it. So let f of x equals 2 plus 3x was our function in A, right? So we're asked to find the average rate of change on the following intervals between x equals 0 and x equals 1. Pretty nice. We're just given the function and 2 numbers, right? So average rate of change. Who can help me out with this one? Can you just give me an answer, Griffin? How do I get to 3? Plug in my x values. What am I plugging my x values into? What am I plugging into? The function, right? What am I going to do with that though? Solve. I'm really trying to get it out of you. F of 1 minus f of 0 over 1 minus 0. That was a really great effort. You guys did great. So right, I'm going to plug in, write down my function by plugging in 1 and 0, my average rate of change, and then so I'm going to have 2 minus 3 times 1. Remember, parentheses are your friends. And, oh, not minus, plus. 2 plus 3 times 0 over, 1 minus 2. Okay, yeah, over 1. So what's that going to be? 5 minus 2. So I'm just given 3. Do I have any units on this one? No, I wasn't given any units. I was just, here's a function, give me the average rate of change. Right, not a word problem, so I don't really need functions. Wow, I gave myself a lot of space. Let me underline these. Okay. Right, so now between 1 and 4. Oh, perfect, we'll get to that space. So I'm going to do f of 4 minus f of 1 over 4 minus 1. And if you want, you can kind of go up to the side. So f of 4 is going to be 2 plus 3 times 4, which is 2 plus 12, 14, just to save yourself a lot of work. 1, which is 5. Right, so then I'm going to get 5 minus, what is that? No, not 5, 12. Yeah, 12 minus 5 over 3, which is, I did something wrong. Oh, I did 14. I meant 14. I had 12 stuck in my head. 14 minus 5 is 9 over 3. And then, surprise, surprise, I get 3 back out again. Thank you, Ronald. So I took an interval that was 0 to 1. So like this big interval, and then this next bigger interval, and they still have the same average rate of change. That's the best part about the average rate of change versus, let's say, the net change, right? My net change of each one of the top one was 3, but my net change in the bottom one was 9. But now average rate of change, every interval is going to go up by 3. 1 unit interval. That's what I meant. Okay. Now, what about if I want you guys to find the average rate of change between x equals c and x equals d? What should we do? This is a really cool one. Would I treat it any different? Or should I still plug in d and c into the average rate of change function? What do you think? Yeah, I'm just going to plug it in just like if they were numbers, right? So f of d minus f of c over d minus c, right? So this is going to be 2 plus 3d, excuse me, minus 2 plus 3c. Oh gosh, what did I do? There we go. Over d minus c. Right, I'm going to distribute this a negative. So I'm going to have 2 plus 3d minus 2 minus 3c. Don't forget to distribute to the second term, right? Over, again, d minus c. Start back over here. 2 minus 2. So I'm left with 3d minus 3c, right? We don't want to just like give this as our answer. We want to clean up, finish our plate, take it to the dishwasher, rinse it off. Don't want to just leave it on the counter like somebody does in this house. right? So what can I do next, right? How else can I simplify this? Am I done? Is it simplified? All right, I'm going to factor. My greatest common factor of each of these terms in the numerator, sorry, is 3. So I'm going to pull the 3 out. So d minus c over d minus c. Well, that's just, those are going to cancel out. This is why we practice simplifying rational expressions. And guess what I'm going to be left with? It's 3 again. Isn't that wild? So even though I'm not given any numbers, I can find the average rate of change of a linear function because it's that special that it's going to be the same number every time. Does anyone else think that's super cool? I think that's super cool. Okay, thank you, Abby. All right, so what does this tell us about the m and y equals mx plus b, right? Because notice our function up here was 2 plus 3x. I got 3, I got 3, I got 3. What does that tell us about m? It's, careful, don't say rate of change. We need to be more specific about what type of rate of change. Right? M is constant, and, oh, wait, that makes sense that it's constant. Wait, hold on. M is our slope, and B, average rate of change, right? And that slope is constant. So constant here, we don't mean like a constant number. It's like a number we call like a constant. But constant here we mean isn't changing. Okay, m is a number, right? We have like 2 more minutes. Ooh, okay, yeah. So with that, I'm just gonna do this one little definition and then we're gonna stop. All right, so if we let f be our linear function, f of x equals mx plus b, we can say I think I want to say, yeah, the average rate of change of f? Yeah, the rate of change. I want average rate of change. Yeah. So the AROC of f is the constant m. And the initial value of f is the constant b. We know these if we've talked about y equals mx plus b as the slope and the y-intercept. But right now, talking about functions, we like to talk about initial values, so when x is 0, and rates of change, specifically the average rates of change. Okay? I'm gonna let you guys finish writing that down. Does anyone have any questions about the constant slope of a linear function and the average rate of change or anything? I haven't opened our exit. Okay. If not, I will open our exit slip. And once you all are finished with that, you are free to flutter away and turn in your homework. Whee! Okay. So remember, you're going to tell me how you felt about today, what you learned today, and then you're going to answer my teacher question. Is f of x equal to 3 minus 4x divided by x a linear function? Did I write 943? Yeah, okay. And then let me check on WebAssign. Oh my God, stay signed in. Clayton, was it you that was having trouble with the WebAssign? Yes, okay. Thank you. See you guys on Tuesday. Have a safe weekend. Right, so exit slip's asking you if it's a linear function. Oh, let me stop recording.